Hi, I'm Belhadj and this is my video lab report. This lab examines constant velocity using a volleyball. The purpose of this lab is to portray Newton's fundamental laws of motion by observing the motion of an object that has a constant velocity, meaning the object moves at the same speed and doesn't change in direction. Then the observational model must be compared to the computational model and conduct an analysis of the similarities and differences between them. Since the object is moving in constant velocity, the position versus time graph will have a constant slope and the observational model and tracker will also have a constant slope, but may differ slightly due to potential errors. Newton's first law states that an object will not change its motion unless a force acts on it. Newton's second law states that the force of an object is equal to its mass times its acceleration. In other words, the force is equal to the rate of change of momentum. The law relates to the total interactions between the system and surroundings to the changes in the motion of the system. The net force is zero when the vector sum of forces acting on the system is zero. Since the object is moving in constant velocity, the net force acting on the object must be zero. To calculate velocity, it is the change in position over the change in time. Here's the video of me rolling a volleyball. In this experiment, the volleyball is the system, and everything outside the system is referred to as its surroundings. Here you can see all the time and position data values. Here's the initial position, and the first two data points were used to calculate the velocity, the initial velocity. And here is the position versus time graph. And here we have the code. I've edited the radius of the volleyball to be 0.105 meters, and I've edited the ball's mass to be 0.27 kilograms. Here we have the initial position and the initial velocity. The initial position is negative 0.09541, and the initial velocity I calculated using the first two data points. Since we know the velocity is the change in position over the change in time, that gave me negative 1.1693. Here I've edited the while loop and set the time to be less than 1.033 because that is the last frame in the video I recorded for the volleyball rolling. And here I've set the net force to equal 0 because that's what the net force is supposed to be when there's a constant velocity. And here, based on the momentum principle, we have the momentum update formula, which is the final momentum equals the initial momentum plus the net force times the change in time. And from that formula, we derive the velocity update formula, which is what we have here. And then we have the position update formula here. The final position equals the initial position plus the velocity times change in time. Then let's run the program. And we have the position versus time graph, and here is the data I used. This is my graph that merges the observed position versus time graph and the predicted position versus time graph. Comparing my observation model from tracker and the computational model, we can see that both feature a downward slope. However, my observational model deviates significantly the more it approaches the end. Frictional forces can play a role in decreasing the speed of an object as it acts in the opposite direction. However, the graph shows that the difference is that it is heading upwards, not downwards. This means that there has been an error on my part because the ball moves in the left direction a tiny bit upon further observation. It is not completely noticeable as it looks like it is going straight, but watching closely, it does deviate slightly. To improve the accuracy of the model in the future, I will make sure that the ball is going completely straight when releasing and is not deviating even a little bit. I filmed the video with the ball moving from right to left. This resulted in a downward slope. Now, if the direction were to be flipped, what would happen? The only difference would be that the position versus time graph would feature an upward slope. The net force being 0 is not entirely accurate, as frictional forces can intervene with the object's speed and cause it to slow down. Also, the object can collide with air particles that contribute to air resistance. Therefore, it is really difficult to enforce the net force being 0 in the real world. Lastly, it is impossible to tell how many forces have to be added to result in a net force of 0 because of these frictional forces. The model can account for frictional forces in some ways, like using a surface with a very low dynamic friction coefficient.